Yeah, what up everyone? It is Mr. Park again. Today we are going through the SRT Refraction file. So if you're with me, stay with me. Let's do this. Alright, so number one is asking you to draw the light rays as it enters this box that has a smaller index of refraction than the outside of the box. So if we're going from a higher index to a lower index, we know that the light is going to refract away from that normal line. So as you can see, this angle is a little bit bigger than that one. I didn't do a great job, but you can still tell that it's refracting away. And then as it's going back to the outside of the box where it has a higher index of refraction, it's going to refract towards the normal line. So that's what your light ray should look like. Right. And then they ask you to find the angle of refraction. And we can do that using Snell's law. And this should look very familiar to what you did during the refraction practice problems. And here with Snell's law, you just want to plug and chug here. So the index given outside is 2, and the incident angle is given as 18 degrees. Is equal to the index inside, 1.3, times the sine of the refracted angle we want to find. Now, I don't like having my variables on my right side, as you know, so I'm going to switch it over to the left side again. So we have 1.3 times the sine of theta 2 is equal to, this actually ends up being 0.68, 2 times the sine of 18 degrees, 618, I mean. So we have that. I'm going to divide both sides by 1.3, algebra. You end up getting sine of theta 2 is equal to 0.475. I'm going to take the inverse sine of both functions, or both sides, not functions. Inverse sine of 0.475, and you end up with the refracted angle being 28.4 degrees. Alright, questions 2 and 3 are what I like to call tandem questions, because if you answer one, you get the other, and if you get one wrong, you'll probably get the other one wrong. But it's asking about a light ray in air, and we know that in air, n is equal to 1. So we're going from n is equal to 1 to quartz, where n is equal to 1.46. So you're going from a smaller index to a higher index. So for example, this light ray is going from a smaller index to a higher index. So as it refracts, it bends towards the normal. So my brain likes to answer this question first because it's visual, and then you have to think about the angle. If the incident angle is this big, and if it's bending towards the normal, that refracted angle should be smaller. Alright, number 4, there's more refraction practice. It's a laser light beam. It's traveling from water, where n is 1.33, into crown glass, where n is 1.52, and I've just drawn this out. I know it doesn't ask you to draw things, but I think it's always beneficial to visually see what's actually happening here. Anyways, the only difference in this problem is they give you the refracted angle, and they're asking you to find the incident angle. So, different problem, but the same formula, where we're going to use Snell's law again. We're going to write that out. n1 sine theta of 1 is equal to n2 sine theta of 2. We know n1 is 1.33. The incident angle is what we're looking for, so we're going to leave that variable there. Second index of refraction is 1.52, and they give us the refracted angle is 34 degrees. And wow, look at that, the variable's on the left side, so I don't even have to change anything. So we get 1.33 times the sine of theta 1 is equal to, if you simplify that, it turns out to be 0.849. Then we're going to divide both sides by 1.33. We get sine theta is equal to 0.639. And we are going to take the inverse sine of both sides so that we can find theta. And we end up getting theta 1. Oops, I forgot to write the ones down. don't forget, theta 1 is equal to, your incident angle should come out to be 39.79 degrees. Okay, number 5 is the exact same problem as number 4, except the only thing we're changing now is that they're telling us that the angle of incidence is 0. So it's completely parallel to the normal line here. So if you've ever wondered what happens when it comes in with the normal line, like parallel to it, then today is your lucky day because we're about to find out. And we are asked to find the refracted angle. And we can do this with, guess what? Snell's law. Wow, it's almost like we use this a lot, right? So we're going to write that down, and 1 sine theta of 1 is equal to n2 sine theta of 2. And once again, the problem might look different, but it's the same plug and chug. Similar conditions. Initial index is 1.33. And now the incident angle they're telling us is 0 degrees. We know the second index is 1.52. And we are asked to find this refracted angle. Alright, so let's do a little bit of math. Sine of 0 is 0. 1.52. Bring everything else down. 0 times 1.33 is equal to 0. Oh my goodness, my variable is on the right side. That won't do. I'm going to switch it over because of my OCD. Please forgive me. Alright, we're going to divide both sides by 1.52. So we get sine of theta 2 is equal to 0. We're going to take the inverse sine of both sides. And if you didn't know what the inverse sine of 0 is, let me tell you, it is, drum roll, 0. So your refracted angle should be 0 degrees. Okay, so for number 6, they're asking how fast light travels in crown glass compared to light in a vacuum. Now to do this, we're going to need conceptually the definition of index refraction, which, if you didn't know, index refraction n is the ratio of the speed of light in a vacuum, which in science we like to call c. It's the ratio between the speed of light in a vacuum times the speed of light in that medium. So in this case, we're going to denote it as x times c because we want to know how fast it is compared to the light in a vacuum. So we have n, 1.52 is equal to, we can cross out these because they cancel, and we're left with 1 over x. As you can see, the math in this is not too bad. We're going to cross multiply. It's the thinking that is kind of hard getting here, which is the case with most physics. This ends up being 0.66, which means that is 0.66 times the speed of light in a vacuum, but we want to denote it as a percentage, so we're going to multiply by 100, and we get 66% the speed of light in a vacuum. That's how fast it goes in crown glass, about 2/3 the speed of light in a vacuum. Alright, for number 7, it's asking, in order to have total internal reflection, light has to travel from A. It is a more dense to a less dense medium. And the answer why is because if you're going from a less dense to a more dense material, if you'll remember, the light ray is always going to be refracted towards the normal, which if we want total internal reflection, we want that light ray to be refracted away from the normal until we get to 90 degrees, which is never going to happen if we're going from less dense to more dense. So, there. And does it work the same way for all indices of refraction? You betcha. Yes, it does. Number 9 is asking us to find the critical angle of light as it's going from emerald into air. So I'm just going to write down our initial conditions here. For emerald, we have N1 is equal to 1.6, and it's traveling into N2, which is air. And it's asking for the critical angle, and we can do that using, I wonder if you guys can guess already, Snell's law. But in this case, it's a little bit special because I will talk as I'm plugging this in. The incident angle is critical, and the critical angle only happens when the refracted ray is at 90 degrees. Alright, let's do a little bit of algebra here. 1.6, I'm going to bring everything down. 1 times sine of 90 is 1. I'm going to divide both sides by 1.6, which should give us that the sine of the critical angle is 1 divided by 1.6. We're going to take the inverse sine of both sides. And that should leave us with the critical angle being 38.7. Yes. 38.7 degrees. Alright, number 10 is asking us to investigate what happens when a light beam has an incident angle of 90 degrees. Now, I'm sure some of you have actually been wondering this in your minds, but let's investigate. And it gives you a little hint. Make a drawing. So let's make a drawing. So let's say we have a boundary between two medium, 1 and 2. And we're used to, so far, light coming in at an angle looks like that, or maybe it might look like that, or even like that. But this one's asking, what if it's coming in like this? 90 degrees. Will it be refracted? No, it won't. It will not be refracted. The reason why is because for light to refract, it has to enter from one medium to another. Where in this case, you can see that it's just gliding along the interface between the two. So it will not refract. Zero refraction.